Our topic for this video is stoichiometry and stoichiometric calculations. Stoichiometry, the word, is derived from two Greek words, stoicheion and metron, which means element and measure, respectively. So under stoichiometry, what we do is we calculate the masses of reactants and products. So in a chemical reaction, we calculate the masses, and sometimes we may have to calculate the volumes if the reactants and products are in gaseous state. Before we start with stoichiometric calculations, we need to recall certain things, like what are reactants? Reactants are substances which we have when we are starting the chemical reactions. So these are substances which we have in the beginning of the reaction, and these are always written on the left hand side. Reactants are always written on the left hand side of the chemical equation. Products, these are new substances formed during the chemical reaction. They have new set of properties. These products are always written on the right hand side of the chemical equation. Between the reactants and products, we always have an arrow. The arrow has to start from the reactants and it should point towards the products. The arrow indicates the direction of reaction, the direction in which the reaction is proceeding. So it has to always start from the reactants and move towards the products. Next, we need to recall about balanced equation. Now, equations need to be balanced because we need to show law of conservation of mass. The total mass of reactants is equal to total mass of the products. This has to be shown, so we always write balanced chemical equations. Now, when we are balancing the chemical equation, we write certain numbers in front of the reactants or products so that the number of atoms on both sides are equal. Now, these numbers are called as coefficients or stoichiometric coefficients. These numbers are called as stoichiometric coefficients. Stoichiometric coefficients. Now, if you see in front of methane, in front of CH4, there is no number written, which means the stoichiometric coefficient here is 1. Here the stoichiometric coefficient is 2. So anywhere you see that there is no number written, that means the stoichiometric coefficient is 1. Then we have the state symbols, which indicate the state of the reactants and products. Now in this example, all our reactants and all our products are in gaseous state. If a reactant or product is in solid state, we write S, and the state symbols are always written in small brackets. If they are reactants or products are in liquid state, we write L. And if we have a solution, if any substance is in the form of a solution, then we write AQ. And of course, we write G if it is. Now let us see how to carry out stoichiometric calculations. This involves a lot of interconversion. Let's see. If you look at this equation, methane burning in the presence of oxygen to give carbon dioxide and water. Now, based on what we have learned in lower classes, we can say one molecule of methane is reacting with two molecules of oxygen to give one molecule of carbon dioxide and two molecules of water. So we know whatever is indicated in a balanced chemical equation is representing molecules of those reactants and products. Now what you need to understand here is these stoichiometric coefficients. These stoichiometric coefficients are not just representing molecules, they are also representing moles. So these stoichiometric coefficients represent both molecules as well as moles. So instead of saying one molecule of methane, I can say 1 mole of methane reacts with 2 moles of oxygen to give, instead of molecule, we can say to give 1 mole of carbon dioxide and 2 moles of water. So the stoichiometric coefficients here indicate both molecules as well as moles. Next, now we know 1 mole of any gas occupies 22.4 liters of volume. It's a gas law, one of the gas laws. Which gas law is this? Leave your answers in the comment section below. So 1 mole of any gas occupies 22.4 liters of volume. So instead of saying 1 mole of methane, since this is in gaseous state, in fact all our reactants and products in this equation are in gaseous state. So everything can be expressed in terms of volume. So we can say instead of 1 mole of methane, we can say it is 22.4 liters of methane reacting with 2 moles of oxygen. That means 22.4 into 2. That will be 44.8 liters of oxygen to give 1 mole of carbon dioxide, that is 22.4 liters, and 2 moles of water, that is 44.8 liters of water. So we can convert moles to volume if the reactants and products are in gaseous state. The next thing is we know that 1 mole of any substance has a mass equal to its molar mass. 1 mole of any substance has a mass equal to its molar mass. So instead of saying 1 mole of methane, I can say methane, molar mass of methane is 12 plus 4, that is 16 grams. So I can say 16 grams of methane reacts with 16 into 2, oxygen atom is 16, you have 2 oxygen atoms, so 32, but we have 2 moles, so 32 into 2, that will be 64. So 16 grams of methane is reacting with 64 grams of oxygen to give 44 grams of carbon dioxide, and 18 into 2 is 36 grams of water. So there are a lot of interconversions happening here. By knowing one, we can convert it to other things like If we know moles, we can convert it to mass. If we know moles, we can convert it to volume, number of moles. We can find out the volume if it is in gaseous state, and we can also calculate the density. So you need to be clear with these interconversions when you have to do stoichiometric calculations. Let's take an example. How many moles of methane are required to produce 22 grams of carbon dioxide after combustion? Whenever you have a question based on stoichiometric calculations, the first thing you have to do is write a balanced chemical equation. If your chemical equation is not balanced, then your calculations will be wrong. So this is combustion of methane. Methane is undergoing combustion. So this is our balanced equation. Now, if you look at this equation, we just now saw we have 16 grams of methane reacting with 64 grams of oxygen to give 44 grams of carbon dioxide plus 36 grams of water vapor. So the question is, how much methane in moles? How much methane is required to produce 22 grams? Now what we have seen here is we are getting 44 grams of carbon dioxide when we have 16 grams of methane. 16 grams is nothing but 1 mole. Now these calculations are like simple cross multiplications. So 44 grams is obtained from 1 mole, 22 grams will be obtained from X moles. So simple cross multiplication, and we get the value of X to be 0.5 moles. Now it's very obvious, if 1 mole is giving 44, then 0.5 will give you 22 grams of carbon dioxide. But if you're writing a CBSE test or exam, if you're following CBSE curriculum, then it's very important you show step-by-step calculations, because the marking scheme has marks for each and every step. So even though it's very obvious, you are expected to show these steps. Okay. So we just need 0.5 moles of methane to get 22 grams of carbon dioxide. Now remember, your answer has to be in moles. You cannot write 8 grams of methane is required, because in the question it says how many moles of methane is required. So you need to answer based on what is asked in the question. I have two practice problems here. The first one is again based on combustion of methane, but the next one is based on combustion of carbon. Solve these questions and leave your answers in the comments section below. Thank you.